Oh no, it's crashing. There we go. So if we think about the differential equation, which is a simple model actually of wave phenomena, but it's x squared times y double prime plus xy prime plus x squared y equals 0. This actually helps us model the sort of phenomena that we were looking at just now with waves. So whatever kind of wave you're interested in, you can, for instance, think of a Wi-Fi signal moving throughout. As you get closer and closer to the Wi-Fi or the router, then you're getting more intense wave fronts than further away, which is, in your experience, you would think you would experience this as the closer you are to the Wi-Fi box, the stronger your Wi-Fi, and the faster your connection. What is a solution to this DE, right? How do we actually model that? A solution is the function, and at first it's not going to be clear that it is a function, okay, but it is. J sub naught of x equals the sum from n equals 0 to infinity of -1 to the n power x to the 2n power all over 2 to the 2n times n factorial squared. Okay, let's think about what exactly is happening here. So this looks kind of like a series. We've been working with series quite a bit. But instead of just expressing things in terms of n, we also have this x. So this is going to have a different value depending on x. Okay, this is called a Bessel function of order 0. I claim that this satisfies the DE. That's what it means for it to be a solution. But what is this function? What does it look like? How do we know this actually exists, right? Because if we think about what this is saying for each x, really what we're saying is this is something that looks like -1 to the 0 is 1, so plugging in 0 gives you 0. Plugging in 0, regardless of what it is, will give you, but let's talk about a general x, right? So the first term for a general x will be x to the 0, so 1 over 2 squared, so 4, times n factorial. 0 factorial is just defined as 1, so we're going to put 1 right there. Plus, and then the next one's going to be -1 times x squared over 2 to the 4th times, hang on, I got carried away, didn't I? That's going to be 2 times 1, so that's going to be 2. And that means this was also 2. And then 1 factorial is 1 times 1. Plus, and then the next one's going to be -1 squared, so that's fine. That's going to be positive. It's going to be x to the 4th over, now this one's going to be 2 to the 4th, times 2 factorial squared. So 2 factorial squared plus ... Okay, so that is, this looks like the function 1/2 plus, sorry, not plus, minus 1/4 x squared plus, now 2 to the 4th is 16 times 4 is 64, 1/64 x to the 4th, and so on. Okay, this goes on forever. It's an infinite series. Okay, so we're actually looking at, is it something like an infinite polynomial function, okay, with increasing powers of x. Notice that we only have even powers of x. That's an important characteristic here, okay. So if we wanted to graph it, it might look like, think about taking the constant function 1/2. Let me draw in real quick, briefly. Think about taking the constant function 1/2. Let's just say that's 1/2, right? And then the next one, we would add a squared term. So it'll be 1/2 minus 1/4 x squared. So it would look something like this. Oops. And then you add an x to the fourth term, and then it'll look something like this. Okay, at the end here, we're going to see what the actual Bessel function itself looks like. But you'll notice that there's some increasing complexity. But in the region close to the origin, we kind of already know what it'll kind of look like, right? Because this kind of pattern here is repeating. And as we'll see, that's no accident. So let's actually get into the weeds here. What is this function, right? So really, this function, for each x value, we're finding the limit as n goes to infinity of s sub n x, okay? S sub n is a sequence depending on x, where s sub n x is the nth partial sum evaluated at x. So k equals 0 to n, negative 1 to the k times x to the 2k over 2 to the 2k times k factorial squared, okay? So the only thing that's different here really is the presence of x. But for each x, we assign this sequence of partial sums. So in other words, we're revisiting the concept of series, but at each different x, has a series definition. So whether you want to think about it as along the x-axis, you have these infinitely many series, or you can think about the function itself as being really a series of functions, not of singular values. And each x value yields you a unique series that we hope converges to some value. So we don't actually know yet that this converges to anything, that this actually confers any value, right? It could be that these values are infinite, right? But I claim that it is. And so if you think about like the sequence of partial sums, right? So sequence of partial sums. The partial sums then are basically formalizing what I showed you in the previous sketch of a graph, right? Which is that your zeroth partial sum, so the first term, ends up being, I claim here that it's 1, not 1/2. What did I do wrong here? 1. Oh, that's because 2 to the 0. Yeah, that's right. Sorry. That's a horrible mistake for me to make. 1. But see, proof that everyone makes mistakes, right? Nobody's perfect. Okay, so the first term of the series is the constant function 1. The second term, indicated with the index of 1 because we're starting at 0, is 1 minus x squared to the 4th. So each partial sum is a finite polynomial function. And each time we get a little bit more complexity. So at this point, I'm just kind of already computed the first few terms here. And you'll notice that the terms are getting smaller. So we would hope that they do get smaller, right? Over 2, 304. Okay, so now we have, so we started with a degree 0 polynomial, then a degree 2, then a degree 4, then a degree 6. And it keeps stepping up in that order. And so on. And really the graph itself is beautiful. And I'm not going to do it any justice here. So I'm sorry that I'm going to butcher it. But it looks something like this. I'm just going to draw 1/2 of it, and then I'm going to mirror it on the other side. Notice that it is an even function. Isn't that cool? So it looks something like this. And that is the particular Bessel function of 0th order that we're looking at. And if you get larger and larger, or a larger and larger n to give you a partial sum, you'll get a higher order polynomial that approximates this much better. So depending on your computational power that you care about, you may be interested in just finding something that looks something like this. And so in a region around the origin, we don't actually care too much about the higher order terms, because our, for instance, if this is, let's see, how many turning points does this have? This would probably be something like this one, or maybe even this one. I was just sketching this freehand, so it's not necessarily accurate. In any case, so we're gonna see this again, a pattern of approximating a function that's really defined in terms of a power series, which is what this is, and by looking at just one of the nth order polynomials, we'll have a pretty good approximation. And so we'll see that notion of approximation, finding error again. Okay, so here's the main important part, okay? So convergence. Because if each function value is defined in terms of a power series, right, then we should know that this value exists, that it converges, right? So claim for all x on the real number line. So for all real numbers x, the Bessel function converges. Okay, so each real number x yields a convergence series for that x. Okay, so let's just look at two. We're going to look at first a very specific case and then a general case, right? So because if we want to really nail this, we should at least see one concrete example, right? So part one, what happens when x equals 0? Okay, and for this one, we don't have to be too rigorous because we're actually just going to see how this expands out into something really nice. So if x equals 0, then by our definition, this Bessel function is going to reduce to the series which looks complicated, and I'm not entirely sure what's going on here, right? But you'll notice that this is an alternating series, and the denominator here is going to give us, so in other words, we have here a b sub n equals 1 over 2 to the 2n times n factorial squared. Is this decreasing? Oh, it's decreasing. It's definitely decreasing. Just look at it. And then the limit of this thing is definitely 0. So by the alternating series test, this converges, right? Okay, great. So for at least one real number, x equals 0, we know that this thing converges. Great. For arbitrary x, so for any real number, right, we'll use the ratio test. The ratio test is going to be really helpful here just because we have that factorial happening in there. And then powers of 2n also we're going to cancel out. So we're going to use L equals the limit as n approaches infinity of a sub n plus 1 over a sub n. So the alternating part gets cut off basically, and we can do x to the 2n plus 1 over 2 to the 2n plus 1 times n plus 1 factorial squared. Okay, so that's the n plus 1th term of the series. Notice the presence of that x there. And then we'd multiply it by the reciprocal of the bottom, right? So times 2 to the 2n times n factorial squared over x to the 2n. Okay, so some nice things are going to happen here, right? Some nice cancellation. For instance, let's just identify some pieces here that we want to work on. So this part here that I'm boxing in magenta, these are the 2 raised to some power, okay? So that part right there, we have 2 to the 2n over 2 to the 2n plus 2. So you get a cancellation that's really just going to give you 1/4. Why? Because these parts cancel, and you just get a 2 to the 2nd power, which is 4. Okay. Then, let's look at this part right here. The x's will also have something similar happening, right? Okay. So x to the 2n plus 2 over x to the 2n, assuming x is not equal to 0, will give us x squared over 1. So x squared in the numerator. Okay, great. The last piece here that is interesting to work with is what happens to these guys right here. So these are squared, okay? So we're going to have 2 copies of something, but we also have that factorial in there. So let's see what's going to happen with that. So we have n factorial squared over n plus 1 factorial squared. We can use our elementary school knowledge of what squaring means, which is basically, what I mean by that is, let's go back to squaring just means multiply it by itself, right? So n factorial times n factorial equals n plus 1 factorial times n plus 1 factorial. Okay, so what is that going to do for us? Remember that when we have an n factorial over an n plus k factorial, we're going to be able to expand out some of the terms. So we'll have an n plus 1 times n factorial times n plus 1 times n factorial. That's all underneath n factorial times n factorial. Okay, don't get too scared of the factorials, right? It's still a number, right? It's something that we can work with. So these are identical, cancel them. You end up with 1 over n plus 1 times n plus 1. You end up with 1 over n plus 1 squared. Okay, cool. Let's put it all together. That means L is the limit as n goes to infinity of, let's go back and see what we had, right? So the magenta boxes, right? Those terms, we've reduced that down to 1/4, and then we've reduced down the blue terms to x squared. So we have 1/4 times x squared times 1 over n plus 1 squared. I mean, squared, not factorial. Squared. So we have the limit as n goes to infinity of x squared over 4 n plus 1 squared. Now, x here is constant in the eyes of this limit, which means it's a fixed value. It doesn't matter. What matters here is what happens as n goes to infinity. Well, the denominator has an n in it. The numerator doesn't. This is a limit that goes to 0. Okay. Notice it doesn't depend on x. That's less than 1. So, by the ratio test, the series j sub naught x, for that x, which is an arbitrary x, any x at all you want. It can be 1, it can be 1,000. It doesn't matter. It will converge. So in our context here, right, this Bessel function has the domain R, more accurately, it's the infinite interval negative infinity to infinity, okay? And as we'll use some more rigorous language in the next video, we would say that this has an infinite radius of convergence, and the interval of convergence is negative infinity to infinity. Now, one note here, the Bessel function having this domain and whether it converges, that's because we've defined the Bessel function in terms of its power series representation, right? So that's where we started. There is a notion of different functions having a power series representation and whether those converge and whether it's equal to the original function itself over the entire domain. And that's kind of where we're headed. So we're going to talk about power series representations of functions in the next section, not in the next video. In the next video, we're going to go over the basic terminology of power series and how to work with them. But that's where we're headed, and we're going to see that some really exotic and crazy stuff happens if we're not careful. But just rest assured that a lot of the examples that we're going to cover are going to be nice and easy and work out just the way we want them to.